Hello and welcome to these notes on setting up and solving projectile motion problems in physics. Before we do the two examples that I've prepared for today, it's important to realize that there are certain rules of the road that I always follow when solving these types of problems. First and foremost is that we will always break up the x and y directions into columns, meaning any velocities, any accelerations, any distances will all be split up into the x direction and the y direction, and you will see me do this via columns. Second, and probably equally important, is that the acceleration in the x direction is always zero, meaning you only get one equation to use in the x direction at any given time, and that is the one that I've just highlighted, which is delta x is equal to v naught x times time. This is the only equation we get to use in the x direction because all of the other equations, when you plug in acceleration of 0, end up being useless. Third, anything horizontally launched will have an initial velocity in the y direction of 0 meters per second, so that means it is launched straight ahead and will have no initial velocity in the up-down y direction. That's important. And finally, just a note is that oftentimes in projectile problems, as you will see shortly, that because you only have one equation in the x direction, the one again here that I've just now boxed in as well, because that is the only x equation you have, it is often in these problems that you will have to solve for time in the y direction and plug that in to the x direction to solve for x or v naught. That's pretty common practice because if you're missing one of the three variables in that boxed equation, you can't solve for anything else if you have two or more of those unknown. So it's really important to realize that you will often solve for time in the y direction before you're able to solve for what you want if that is in the x direction. So, with those four rules in mind, let's go ahead and try some problems out. Alright, let's start off with example number 1. A rock is launched off of a 30-meter tall cliff at 20 meters per second horizontally. The first thing you need to know is that the rock moves 30 meters downward from the top of the cliff, meaning that the cliff is 30 meters tall. We've got that right there. And then the second thing we need to note is that it's launched horizontally at 20 meters per second, which means it's going to be shot off horizontally, something like that, and it's going to sort of arc downward like that. Okay, nice and easy. So my approach to doing this is going to be pretty simple. I'm going to start, as always, by breaking this page in half, maybe a little less dramatically. There we go. And I'm going to break this up into x and y stuff. So I'm going to have givens for the x side of the equation, and I'm going to have given information for the y side of things. And I'm immediately going to write down our one equation for the x component. Because remember, this is the only equation you get to use, so I'm going to put it down because that's essentially given information at this point. So, I'm going to start by filling in what we have, what we can see here before we do anything, deal with anything that's sort of hidden or invisible. So 30-meter tall cliff means that the object is going to drop 30 meters. And because the object is going in the negative direction, I'm going to say that my delta y is a negative 30 meters, meaning that the object is moving down. That's what I'm allowing this negative sign to mean, is that the object is going in the downward direction. And I'm going to sort of make a reminder here that this way is negative and this way is positive, or you can set it up however you want. That's just how I'm choosing to make my positives and negatives. So just a reminder there, it's off in the corner. The next thing I know is that it's launched horizontally off the cliff at 20 meters per second. So the horizontal part tells me that my v naught in the x direction is going to be 20 meters per second. That is what that tells me right there. What this also tells me is that the buzzword horizontally, going with my drawing here, means that we are going to have no v naught in the y direction. It is 0. There is no vertical component to my launch. So at this point, we've got 3 pieces of given information, but there's of course one more that we always use, and that is the acceleration due to gravity, or the acceleration in the y direction, depending on how you want to notate that. And that is going to be negative 9.8 meters per second squared. Again, the negative meaning that it's going down, just like our delta y. So this is really what we have. Okay, we've got 3 givens in the y and only 1 in the x. So currently, because we don't have this delta x here, we have 2 unknowns in the x direction, and therefore we're kind of stuck on that side. There's nothing we can use on the x direction side to solve for anything. That means we have to use information on the y direction. So we need to pick an equation. We've got a couple to choose from. We've got this one, which looks kind of like that. We've got, of course, the delta y equals the Voigt plus the 1/2 at squared. And we have the final one, and we've got v equals v naught y plus at. So we've got some options here. Now, notice, immediately right off the bat, we do not have vy. We do not have that number or that number. So these two do not work. This one on top especially will not work because there's no t in the equation. That limits us to this middle equation right there. It's the only one that does not have vy in it because we don't know what vy is. We don't know how fast it's falling at the end. We don't know. And it's the only one with t in it. So by process of elimination, we're going to use the equation boxed here in green, which is going to be delta y equals v naught y t plus 1/2 at squared. Going to rewrite it. And lucky for us, because the v naught y here is 0, this whole part goes away, because 0 times whatever t is just going to be 0. So that simplifies our equation, and now at this point we can plug in our numbers. Negative 30 equals 1/2 times negative 9.8 times t squared. Now notice how, because we have 2 negatives, the negative on the left and the negative on the right, that those two will end up canceling each other out, which is really nice because it'll give us a positive time. Obviously, positive time is what we are going for in a problem where you can't go backwards in time. So with a little bit of plugging into your calculator, you end up getting a time of 2.47 seconds. Boom, right there. There is our time. And we do that, of course, by doing some algebra, by dividing over the 1/2 times negative 9.8, and then taking the square root. So there's my time, which is what we're looking for in part A. And part B is asking, where does it land? And where is going to kind of be code for delta x. Now the good thing here is the time in both columns here ends up being the same, which is convenient. It means that we can go over to the left-hand side and plug in 2.47 seconds. And now it's just a matter of multiplying. So we have 20 times 2.47. And when you plug in 20 times 2.47 into a calculator, you get a distance of 49.4 meters. So there's our second answer for B. Now, if I wanted to make this problem just a little harder, what I could easily do is just ask problem B, where does it land? And in asking just B, you as a physics student and physics doer would need to see, oh, I'm missing this variable of time, I don't have it, so I need to go over to the y side and solve for it. And you would do the same exact problem, except you wouldn't have that sort of middle step of letter A to kind of guide you in the right direction. So that would be a little trickier if I wanted to do that. Cool. So that's an example of a horizontally launched projectile. All right, let's take a look at a problem that's a little bit more of a traditional projectile problem in that the object is launched at an angle. So if we read the problem here, what we end up seeing is that a golf ball is hit at an angle of about 20 degrees with a velocity of 21.7 meters per second. It lands on the ground below the cliff 5.48 seconds later. How tall is the cliff? So we're looking for how tall it is, or what is the delta y that this thing has traveled. And we're looking for how far from the base does it land, or our delta x. So how far out did the golf ball actually travel during this time? Now, this is obviously a slightly more complicated problem because we're dealing with an angle. However, our approach is going to be the same. It's going to be to draw this out, which I did while I was explaining the problem, break this into two sides, the x side and the y side, write out our givens for both the x and the y, and go about solving it. Now, in regards to the given information, obviously we know our delta x is v naught xt equation will still be the only equation we can use in the x direction. But with the velocity, we obviously are going to have to do a little bit of trig. So this video is not going to go over the trig rules and how those are derived, but at this point you should kind of know that when we're solving for the v in the x direction of these problems, it's going to be the velocity times cosine of the angle. And when we do it for the y direction, it's going to be velocity sine of the angle. And again, that just has to do with drawing out the trig and doing some SOHCAHTOA, which I'm not really going to do in this video. That can be a discussion for some other time. So just know that the x direction is going to match up with cosine in these problems, and that the y direction will match up with sine, and again, SOHCAHTOA. So with v naught, we're going to plug this in, 21.7 times the cosine of the angle. And on the other side, of course, we're going to do 21.7 times the sine of the angle, which again is 20. Going to just write that in. Don't know why I didn't do that over here, but let's do it right now. Because 20 degrees is less than 45 degrees, what we should end up with is a number that is bigger in the x direction than it's going to end up being in the y direction, which is what we end up getting when we plug this in. I got 20.39 meters per second for my x, and I got 7.42 meters per second in the y. Now, that's helpful. The second really helpful piece of given information here is the time, because we can use the time both in the x direction and in the y direction, which is really nice. Again, it's not something that often happens, but we're going to enjoy it when we got it. Finally, we know that in all of these problems, again, we have an acceleration of negative 9.8 meters per second squared. And again, the negative tells me that it's being pulled downward. So, the first question is, how tall is the cliff? What is our delta y? There's only one equation that will work, and again, it's the one that does not have the final velocity, because we do not know what vy is. We have no clue, and we're not solving for that. So, we want the equation without that in it. So here is that equation. This time, unlike our previous example, we will have to solve, we will have to plug in for that v naught y, but it's pretty plug and chug. 7.42 times 5.48 plus 1/2 times negative 9.8 times 5.48 squared. Now, again, at this point, the positives and the negatives are really important. That negative 9.8 is going to ensure that we get a final answer that is negative, because the golf ball is moving a negative distance, a distance in the negative direction downwards. So it's really important to have that negative in there, otherwise you will not get the correct answer. So doing a little bit of plugging in here, you get the first part of this equaling out to being about 40.66 if you just do that multiplication step. So that's going to be 40.66. The back end of this, with the negative in place, is going to come out to being negative 147.15. And when we do that math, 40.66 minus 147.15, or plus a negative, depending on really your philosophical bend there, I suppose, you end up getting negative 106.49 meters for your delta y. That means the golf ball traveled a negative 106.5 meters. Now, depending on how picky people tend to be with your physics, you could argue that the cliff itself is a positive 106.49 meters tall, but really it's all sort of semantics here. You know that if the golf ball traveled from the top of the cliff to the bottom and it moved negative 106.5 or negative 106.49, that is how tall the cliff is. That's just logic. So I'm going to leave that as my answer. If you really wanted to get picky, you could change it to a positive to represent how tall the cliff is more, I guess, correctly to what we'd expect, but I'm just going to leave it. Secondly, how far the golf ball went, that's nice and easy to do too, because we have both of our variables on the x side. So it's going to be 20.39 times 5.48. Sorry for it being kind of squished. So when we plug that into our calculators, you should get a nice positive number. The golf ball does not miraculously go backwards. There's nothing negative there. And you get 111.74 meters as my distance that it has traveled in the x direction. So there we go. Again, it's a little bit trickier because obviously you have trig. Trig was something that for a long time I struggled with in high school, so I understand that the trig part here can be a little complicated. But ultimately, if you follow the steps by breaking things into x and y's, writing out all of your givens, realizing that there's only one equation in the x direction you can actually use to solve, then you end up really sort of limiting yourself and giving yourself a lot of lines to kind of color in. And it really makes this type of problem a lot simpler to solve when you have those constrictions kind of telling you which way to go. Alright, I hope this has been helpful. Thank you for watching.